You can also make the convergence criteria stricter just in case you want to achieve higher amount of um, um, convergence, because you notice that okay, the convergence criteria according to this criteria has been met, but still there are imbalances. In that case, you can switch off all convergence criteria checks and you can keep on iterating to the level, to the number of iterations that you want. You can also make it simple by saying the convergence criteria should not be checked at all. So in that case, it will keep on iterating as long as the number of iterations are valid. What this number of iterations are will be discussed in the forthcoming slides. We can also make the individual convergence criteria stricter in this case. So there are different ways in which you can deal with stricter convergence criteria. Let's look at situations when we have having difficulties with convergence. So convergence difficulties manifest themselves usually in two ways. One of them is called the blowing up of the solution. So solution is diverging, the equations start, residuals start climbing up. That's very hard sight to see usually. And the other case is when the residuals are not changing, but still there are imbalances, as we noticed. That's when we can make the criteria a bit stricter, but the residuals are not falling down. Then this is usually encountered in highly compressible flows. You usually encounter in highly compressible flows some blowing up, but also in some cases residuals are somehow stuck up, or they are constantly at some level, although there are imbalances in the equations of the different flow quantities. So for compressible flows, multi-phase combustion, usually you encounter this. There are some ways you can troubleshoot them, but it's usually the experience which teaches you the best. Usually you should always check whether your problem is well poised, whether the boundary conditions are well defined, whether this is really what happens in the reality, or is it something very virtual, too virtual, that you're trying to simulate. In that case, surely the solver will complain about it. And whether the mesh is of good quality, this is also something to be checked. We should check whether the initialization is good. With the hybrid initialization option available in ANSYS Fluent 13, this problem should be solved. Once the initialization is also done through let's say the hybrid initialization which is available in Fluent, or you use an initial solutions file from the previous course mesh solution, what we can do it we can start with a lower order discretization scheme like a first order scheme, and we try to achieve certain amount of convergence, and then we go for a higher order upwinding scheme or discretization schemes. Apart from this, the under relaxation factors URF or Courant number can also come handy. I'll just explain this in the coming slides. The under relaxation factor actually comes into picture because of the non-linearity being neglected. So because of the non-linearity of the equations, the residuals might start climbing up if you use a very high value of under relaxation factor. A very high value of under relaxation factor means that the phi which you are using is exactly equal to the phi which you have just evaluated from the previous iteration. But what Fluent usually does is it under relaxes it using a factor that it does not use the new value of phi for the subsequent iteration step, but it uses a change with respect to the previous one. So this is how you can control the convergence of your problem. This comes up mainly because of the nonlinearity in the advection term of the PDEs, which is neglected to convert it into linear algebraic equations. The default values are usually good for a wide variety of problems of these under relaxation factors, but we can modify them. If you make it higher, then this can become very unstable, but maybe it becomes quicker. If the initialization is good, usually it should achieve convergence very quickly. But on the other hand, if the values are too low, it might momentarily show you some lower values of the residuals, but this doesn't mean that your solution is converged. So you should usually try to have the values somewhere around the default values which are anyway available. It's actually the experience which teaches us the best how to play with these values. But usually if you're having difficulties with divergence of your solution, you can try to reduce the momentum under relaxation factor by in steps of zero point 0.1 and still play around with if you're having a two equation turbulence model of k and epsilon, then you can try to reduce the k and epsilon under relaxation factors as well slightly. Conjugate heat transfer problems in which there is a sudden change in the conduction coefficient values from one cell zone to the next, there you might have difficulties with convergence, especially of your energy equation. In that case, you might So it's usually experience which teaches us, also concerning conjugate heat transfer problems when there is a fluid domain and a solid domain, how the energy equation under relaxation factor can be reduced from the default value of 1. Even in multi-phase problems, you might consider reducing the volume fraction under relaxation factors. If it's a density-based solver or a pressure-based coupled solver also, sometimes you might need to reduce the under relaxation factor by some values. So the default for implicit kind of formulation for density-based solver is 5. You can work with a lower value in case you're having difficulties and slowly increase it. For an um, uh, explicit formulation of the density based solver, the Courant number is 1, which you start with. Usually you should not use a value higher than 2. It should be rather on the lower side. Now, ANSYS Fluent 13 has introduced a new feature in its uh, methods of solving the problems, something which is inspired actually by the CFX methodology, that even a steady state problem is approached in a pseudo transient formulation. So what they can do is that we activate the pseudo transient method by which we can do a time marching to approach the steady state solution. So we can proceed in some steps of time. So we can specify these pseudo time steps either, or else we can use an automatic method by which the solver automatically finds out what is the most robust time step to be used for your given problem, and that is the safest method. But a quicker alternative is to use a specified pseudo time step. This is something which is very much part of CFX methodology. CFX has only this methodology, but Fluent offers different kinds of possibilities for its pressure-based couple solver now. These are the three things we are trying to harmonize. The trade-off is between convergence, speed, and accuracy. So usually when we want the solution to be converged, we are looking for a robust scheme, robust formulation. The solver should not crash. But at the same time, if you're looking too much for robust schemes, we might sacrifice on memory and accuracy, and it might need more time as well. So once the process is that we try to achieve convergence even at the cost of accuracy for the beginning, and then once the solution is converged, then we start worrying about the accurate solution, because converged solution doesn't yet mean accurate solution. So we try to go for a higher order scheme. We try to compare the results qualitatively and quantitatively with physical principles or experimental data if they are available, and ultimately, of course, we try to go for grid independence. This means we try to adapt the grid, or we try to refine the mesh going back to the pre-processing stage to get a solution which looks very similar to what we expect through experimental means. If we are having troubles, the usual practice is to check our physical models, if we have included the necessary physical models, if the boundary conditions have been well defined. We check for the mesh quality, and especially we consider remeshing because of the boundary layer capture, whether the Y plus requirement is being met. Just to remind you, the Y plus requirement says that your first cell height should be such that the Y plus is either less than 5 and you're using the enhanced wall treatment in Fluent, or else your Y plus is more than 60 and then you are using the wall function approach for near wall treatment. And additionally, of course, you should also consider whether the boundary's location is right, whether the domain has been considered wide enough, and such problems occur especially due to reverse flow at the outlets, which can cause a lot of convergence difficulties. So we are looking for very quick solutions and accurate solutions, but we have to also be aware of whether we are physically making sense of the problem that we are trying to simulate on a computer. Just to summarize the overall procedure in solver mathematics, we start with usually a more robust, even if it's not so accurate, and quicker numerical scheme, first of all, to achieve convergence. And Fluent's defaults basically aim for this. Once the final results are computed, we try to use the optimum numerical schemes to go for higher accuracy. The accuracy depends whether we have included all the necessary models and whether the numerical schemes are quite good. Basically, CFD is a iterative process, so we always learn from the mistakes, we learn from our bad experiences, and we go on to have more accurate predictions in future. So now that we are familiar with the solver mathematics, let's move on to the post-processing features in Fluent. The post-processing features in Fluent, just to give you an overview, there are different possibilities. We are going to look at those possibilities, what all things we can extract qualitatively and quantitatively. We'll understand what are these color plots, contour plots, how to make sense out of them, and also in terms of numbers. And we'll see the general methodologies, general steps that are followed in doing post-processing. Before that, just to have an idea about post-processing in ANSYS CFD, both in ANSYS Fluent and ANSYS CFD Post, which was earlier CFX Post, which has now been made the general post-processing tool for CFD products of ANSYS. The general one, the ANSYS CFD Post, is surely much more advanced with many options, many functions, many advanced features like volume rendering, lot of animation features, but it requires a separate license. ANSYS Fluent's inbuilt post-processing tools are also quite well developed, especially in the subsequent releases. They are trying to improve them, especially for the users who only have Fluent licenses. It is limited as far as different function calculations are concerned, but if you know the physical, know how to make sense out of the numbers which are provided in ANSYS Fluent, you can also do, we can try to make up for the lack of ANSYS Fluent's post-processing features with some manual or external level calculations. The general methodology which is followed in post-processing in Fluent is the following: that we first of all prepare some locations. Locations can be points, lines, planes, some isosurfaces on which we want to extract data and on which we want to plot data. We want to analyze the data on them. So we first of all prepare such locations. Once the locations have been identified, we go on to identifying the variables. So either the variables can be the ones which are already available in ANSYS Fluent, which are either the default variables or some derived variables, some standard variables. We can also generate our own functions like custom field functions, which we can then plot on these surfaces, or we can extract data. And once that is done, we try to generate some qualitative data at some locations, and on the contour plots basically represent such qualitative data, and we can also extract quantitative data at the locations. That was overall process of ANSYS Fluent, how to do a post-processing. We can specifically look at how to prepare those locations. So the locations can be things like points, lines, planes, and isosurfaces. This is done by going to the surfaces option on the main menu bar, and it can also be achieved by clicking on one of the graphics options that we have here. We can click on one of the surfaces and we can create surfaces within them. This is a new feature available since ANSYS Fluent 12. And the point, if we click on any of these options, what we end up having is, if let's say I want to create a point, such a point dialog box starts and opens up, and we can create points. We can give the locations ourselves, or we can also click on the select point with mouse, and with our right mouse button, which is a probe button, we can click on a location inside the mesh where we want the point's coordinates. So this can be very well used to find out the coordinates of any location on your mesh as well. The next option which can be used is to create lines. So we can give the starting point and ending point, and we can give the XYZ coordinates. Again, point, we can also select the points using the mouse button, and we can create such lines along which we can plot some profiles. Some graphs can be plotted as well. We can also create some surfaces. We need to, in that case, provide 3 points, the coordinates x, y, z of 3 points, or we can also align them according to some surfaces, and we can create planes on which we can generate some data. And also, of course, we can create isosurfaces of either mesh related quantities or pressure or static pressure. We can create isosurfaces. Let's say I want to create an isosurface of let's say velocity, and at that point I want to check for the temperature. So in that case, I can generate such surfaces first of all, and I can plot in the contours plot. I can plot on that surface the temperature plot. This is very helpful if you want to analyze, say, in heat transfer and ventilation, air conditioning, um, kind of analysis to be done for HVAC studies. People generate such velocity isosurfaces, and then they analyze the temperature contours on such surfaces. It's very helpful to have an overview of what are the different temperature distribution inside the room or inside a domain at specific velocity surfaces. once our locations are generated, we try to identify the variables. Now Fluent has some standard variables. Standard variables are the UVW, pressure, temperature, and such variables which are solved for using the transport equation. There are some other variables which are derived from the standard variables, like the dynamic pressure, molar concentration. These are all dependent upon these quantities which are calculated anyway through the equations. But you can also generate your own custom field functions. So some of these quantities you can see here is, you can say, contours of temperature, and actually once you select temperature, then what goes on is we can select what kind of temperature do you want, the static temperature or the total temperature. So you have a lot of derived variables available in ANSYS Fluent as well, and you can plot them on different surfaces, either isosurfaces or the locations which you have just generated in the previous step. You can also generate some custom field functions. You have to go to define custom field functions, and we can create some own custom field functions which you can either use for calculations or you can use for plotting them on specific surfaces. This is very helpful. Let's say I want to plot swirl number on a specific surface, so I can define a quantity called swirl number using the appropriate custom field function, and I can plot it on different surfaces within my combustor or within my swirling equipment. Some of the solution data are pressure, velocity, temperature, turbulence, and species, and within them you can see we have static, dynamic, total pressure, we have velocity, magnitude, or the XYZ components. We can also have a stream function, vorticity, helicity are also included. You have the temperature data, which has static, total, enthalpy, internal energy, entropy. In the case of a rotating domain, you also have rothalpy. For turbulence, we have kinetic energy, dissipation rate, vol y plus, different kinds of quantities which are available all within the standard variables that we are solving for using for dependent variables. And we can post-process them on isosurfaces. We can create some vector plots as well. So can we also generate contour plots, some path lines or streamlines depending upon whether it's a steady state flow or not. We can also generate XY plot, and some animations can also be created in ANSYS Fluent. These are some of the features available. And this is just a snapshot of some of the examples. This was CC Tech's classroom, where we used to take the lectures before we moved now into online lectures. So this is one of the simulations which we performed. This is just showing you the vector plots around the fan and along the candidates who are sitting down on the floor, on the chairs here. And the door used to be somewhere here, and this was an exhaust fan. There was a window here, and we had some furniture inside. And what you can see is, like, we have been simplified the domain quite a lot. And this was the projector which used to project on the screen here. This is the vector plots you can see around the rotating fans. So multiple reference frame kind of problem was solved for the analysis, heat, ventilation, and air conditioning analysis of this room. Through the for internal flow applications, you can see such contour plots. This is a pressure contour plot. You can see the pressure is quite high, but along the curvature the pressure starts dropping. You can also see path lines here. So this is very helpful to visualize the flow inside the domain as well. We can also generate 2D plots. So once the line has been generated or some curves have been created on which we can plot velocity, let's say at the outlet I want to see the velocity profile at the midpoint, then in that case you can see from the no slip velocity value of 0, somewhere in the middle you have an average velocity. So it's more or less like a very uniform flow which is coming out. This is not the best example. Usually you should have more cells near the wall, so there should be a finer mesh somewhere near. In this case it's just for demonstrative purposes we created this plot, but usually you should have finer mesh. This is a representation that the mesh is not so fine. These points represent the cell points which are there on the outlet, on the mid surface. So once you create these mid surfaces, you go to XY plot on the plots option, and we can generate such velocity or pressure plots on them. So once the qualitative post-processing is known to us, let's also have a look at what we can do quantitatively. So we can report fluxes, we can report forces, we can calculate torques. So we can, in this case, for example, we can generate mass flow rate. We can see the fluxes across the inlet and outlet in terms of total energy, heat transfer as well. Total energy includes the thermal as well as the mechanical energy. Forces we can calculate, and we can also find out quantities at the surfaces in terms of area weighted average or mass weighted average. We can find out flow rates. So all these quantities can be either displayed on the screen on the terminal emulator, or we can also create an output parameter which can then be accessed onto the workbench. So Fluent offers a variety of options to do a quantitative post-processing either as a standalone entity as well as integrated within ANSYS Workbench. Just to summarize, ANSYS Fluent has several features to analyze the results qualitatively as well as quantitatively. Basically, this is the aim of any fluid flow analysis, that we want to visualize the flow. The second thing is to find out the effect on the boundaries. For that, we have the quantitative studies available in ANSYS Fluent, and it helps us qualitatively as well as quantitatively to validate our numerical model, our CFD problem, whether we are on track with the real solution. And analysis helps us to define what we should change in the design for the existing model, go back, make some modifications, come down, and have better designs for efficient product development. So post-processing is actually an art, and it is quite heavily priced in the CFD industry. So this is one of the most expensive part of a CFD project. So you should be aware of it, that post-processing requires much experience and also good insight into what is happening inside the domain, so that we can report it to a layman in terms, not in terms of the mathematics that we have learned in CFD, but more in terms of what would physically make sense for the clients. So post-processing is an important and integral part of the overall CFD analysis, which ultimately gets communicated to the outside world from the CFD community. So I'm very thankful for your attention for this lecture as well. It's one of the last lectures we are having for you, and I hope overall CFD course which we offered through this series of lectures was helpful, and that it will give you the right direction to start on with learning CFD. As I said, CFD is something which you learn through experience, because it's an iterative process, it's an art, and it's also challenges you to explore yourself regarding the physics as well as mathematics of fluid flow and heat transfer. Thank you very much for your attention all throughout, and I wish you all the best.